Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
What?
Sicilian. Italian.
So, she is here for 3 months with us as an intern, and she has been working a lot on markets and auctions, and she's giving us a talk on a very cool new result, which is called computing with selfish agents. I think it just got into some.
Yeah, that result is called derandomization of auctions. Okay, so is the mic on, or should I not worry about it?
You should make sure that it's on. Is it?
It's switched on, but
It's switched on. Are there any lights on?
No. Okay, so I thought I'd start this talk with a slide that's a little bit about what I do. And so my two main areas of research in my graduate career have been in economic aspects of algorithms, and that's what I'm going to focus on in this talk. And I've also spent quite a bit of time studying approximation algorithms. Here are some sample problems that I've worked on, and I'd be happy to talk to you about them after the talk if you're interested. So let me move on to the main point of the talk, which is the setting of computational economics. In the computational economics problem, we have a set of independent selfish agents. So throughout this introductory material, I'm going to keep a running example in your mind in which you have a piece of art that you would like to sell to one of several bidders. So here the independent selfish agents are the art collectors, and the task that you want to solve is to allocate this work of art to one of the art collectors. In order to do this, you're going to design an algorithm, which we call a mechanism. And the mechanism solicits some inputs from the agents, and it outputs an allocation and a payment function based on the inputs of the agents. This problem arises a lot in practice. There's tons of very motivating examples from the FCC spectrum licenses, where the governments auction off spectrum for cell phone companies, and then there's the FAA takeoff and landing rights. So in America, they're trying to auction off takeoff and landing slots at airports instead of the current system, which is to just have them grandfathered in. Then there's eBay and Google AdWords, things that you're all very familiar with. The electricity market, and the National Residency Matching Program, and there's many other examples here that I'd be happy to talk about with you later. So let's look at the mechanism design problem a bit more formally. It has two main components. First, you have the agents, and we assume that each agent has a utility function which indicates their happiness for any particular allocation and payment that the mechanism outputs. And the goal of the agents is to report a utility function, or to report information to the mechanism in order to maximize their happiness. So in our running example of the art auction, you can imagine the following utility function, where every agent has some valuation for the work of art, and their utility for a particular allocation and payment is their valuation minus the price they are charged if they get the work of art, or 0 minus the price they are charged if they are not allocated the work of art. So in particular, for him to have positive utility, you would hope that the price is 0 if he's not allocated the work of art, and is less than his valuation if he is allocated the work of art. So the other main component of the mechanism design problem is the mechanism itself. This is the algorithm that, given some inputs, which it solicits from the agents, is going to compute an allocation function and also a payment function. So given the inputs from the agents, it's going to compute an allocation for every agent and a set of payments for the agents. And the goal of the mechanism is to optimize some global objective. And these global objectives vary from problem to problem. Some people consider the social welfare objective, so they want to output the allocation that maximizes the sum of valuations of the agents. So this makes sense, for example, in the spectrum license auctions, where the goal of the government is to give the spectra to the companies that can utilize it to the most beneficially to the population. So to the companies that have the true highest valuation for the spectra. Another objective that's perhaps more familiar to us at Microsoft is revenue maximization. So here you want to allocate the items and charge the agents in a way that's going to maximize your revenue or sum of payments. So in our running example, you can think of a second price auction for this work of art. Here, the allocation function is you ask each agent his value for the work of art. You look at all of the inputs that you get, and you allocate the item to the agent with the highest reported valuation. And then you charge a price equal to the second highest valuation to the agent that received the work of art. Okay, so 2 points about this mechanism. First, you can see, it's not too hard to see that agents will maximize their utility by reporting their true valuation. So that's regardless of what the other agents do. If you underreport your utility, you risk going underneath the second highest bidder, and if you were the highest bidder, you risk going underneath the second highest bidder and losing the work of art when it would have been valuable to you to have it. And if you overreport your utility and you weren't the highest bidder, you risk going above the the highest bidder, and you might get some negative utility by getting charged a price higher than your true valuation. So since we know that agents, no matter what other agents do, a rational agent will report his true valuation, we can claim that the item goes to the agent who values it the most. So this mechanism is maximizing the welfare. Okay. In the argument that I just gave you for that this second price auction maximizes welfare, I was relying on the fact that I knew how the agents would behave, how I would expect the agents to behave. So this raises the issue of equilibrium concepts. We want to analyze these mechanisms and prove properties about them as assuming the agents behave in an equilibrium. So for every agent, you have a set of strategies. For the agents, they submit a set of strategies such that each agent's strategy is his best response to the other agent's strategies. And there are many different equilibrium concepts. The one I'm going to focus on in this talk is dominant strategy equilibria. So I want it to be the case that for this mechanism, it's an agent's best strategy is an agent has the same response to every set of strategies for the other agents. So there is one strategy that's dominant for that agent. It means that no matter what the other agents do, this agent should follow that particular strategy. There are many other solution concepts that are considered in the literature, most of which seem to have something to do with Nash. I won't talk about them here, but they have some benefits and some drawbacks. First, dominant strategy mechanisms are nice because you make no informational assumptions about the agents. You don't require them to know like the distribution of the other agents' valuation functions, which is the case for Bayesian Nash, or the strategies of the other agents, which is the case for Nash solution concepts. So there's no risk of being wrong about that the agent might be wrong about his assumption about the other agent's strategies or valuation functions. So knowing that we're looking for dominant strategy mechanisms, we can in fact restrict ourselves to looking for mechanisms in which it's a dominant strategy to tell the truth about what your valuation is. And this comes from a very powerful principle in this field called the revelation principle. It's fairly easy to state, or even to see why it's true. So since we know that, we suppose that this mechanism is a dominant strategy mechanism. It means that inside the head of each agent, he's taking his true value and he's feeding it into some little pink algorithm and outputting his dominant strategy. So if we want to construct from this mechanism a truthful dominant strategy mechanism, we can simply move this little pink computation outside the heads of the agents and incorporate it inside the mechanism itself. So now, for every agent, they should submit their true valuation because the mechanism is doing the computation that figures out the dominant strategy from the true valuation for the agent itself. So now it has become a dominant strategy for every agent to report his true valuation. Okay, so well, the mechanism announces its rules. So you know the algorithm that the mechanism is computing. So here it would say that I'm doing this computation. I'm doing this pink computation. And you should trust that the mechanism designer is implementing the rules of the mechanism as stated. So the revelation principle says that without loss of generality, we can restrict ourselves if we want to find mechanisms that satisfy a particular solution concept, like dominant strategies. We can restrict ourselves to incentive-compatible ones, or those in which revealing the truth satisfies the equilibrium concept. So for dominant strategy incentive-compatible mechanisms, these are called truthful mechanisms. The theorem I showed you didn't rely on the solution concept being dominant strategy. It would have worked for Nash or any of the other solution concepts that I had flashed on that slide. Okay, another powerful theorem from this field that we're going to use a bit in the talk is the notion of bid independence. So I call an auction bid independent if there is some function which can depend on the bidders, such that that an agent wins 1 unit of the good at price pi equal to this function whenever his bid is at least pi. And this function is independent of his bid. Okay? So I have a set of bids. I cover up the bid for a particular agent. I compute some price for that agent based on the other people's bids. And then I say that the agent wins if his bid is at least that price. And there's a theorem that says an auction is truthful if and only if it is equivalent to a bid-independent auction. So a bid-independent auction is truthful is pretty easy to see because the price that's being computed doesn't depend on your bid, so how could you help yourself by lying about your bid? That a truthful auction is bid-independent, well, this you should do some work, but as an example, you can see for the second price art auction, this is the bid-independent function that would compute the second price art auction. So the bid-independent function for every bidder is to compute the maximum of the other bids and offer that as the price to the bidder. And in ties, we can break arbitrarily. So if you have 2 maximum bidders, it's not a problem because you can break the ties arbitrarily. Okay. That concludes the sort of introductory part of my talk. So now I would like to, yeah?
So an assumption, one of the big assumptions is not to really say value independence, but value doesn't depend on what you pay.
Yes.
It's something we need to worry about for online auctions, right? I should think you could pay more. That this is my utility. But all of these models aren't going to work on
The assumption is that one bidder's utility for the good does not depend on another bidder's utility for the good.
Well, except that my overall utility depends not only on the utility of the good, but how much I can.
You are another bidder, or?
Yeah. You and I are competing. And if you win the pain, that's great. But if you have to pay more for the pain, that's good for me.
Why do you say so?
It's a repeated auction.
Think of a,
He wants to run you bankrupt.
You use your money for this option.
Right, right. So if you're thinking of the case of a repeated auction, I guess.
let's say that we're to do painting stuff, right? And we're competing. It's my interest that you don't make much of a profit. So if you get the painting,
Why?
you know, if I can run her out of business.
Right, well, you're assuming that there's something like repeated auction that,
You're right, you just need
sure.
and get value out of the need.
Yeah, yeah. So this is a.
One of the big examples in which he would really get value out of being mean would be a repeated auction like we have in,
But the general.
No, only in the feed. Otherwise, you don't get more business. Your life is gone. Only
So it
I
is.
mean, it doesn't have to be a repeat. It can be repeated something. Yeah, also competing somewhere else.
right.
Then you have to eat after.
But the type of utility functions that you're interested in are modeled as spiteful bidders. They call them spiteful bidders. And you can say that the utility function, your utility is a function not only of your allocation, but also of everybody else's allocation and payments. And there have been recent works that look at the properties of first and second price auctions with spiteful bidders. But in this talk, we're
Talking about spiteful
you are right that in this talk I'm assuming that your utility doesn't depend on others.
And if you destroyed her talk, it would be.
No, but it's not project.
Okay, so in the types of auctions I'm going to be interested in are auctions for digital goods. So the scenario is that the seller has an unlimited supply of a single good, like a piece of software that he can just copy for free. And he being Microsoft. And agents are interested in at most one copy of the good. The goal of the auctioneer is to sell the items in order to maximize the revenue. And this is the obvious objective that you would want here, not just because that's what you're interested in Microsoft, but because if you wanted to maximize the welfare, your only thing you could do would be to give the item to everybody at zero cost because you have an unlimited supply. So there have been several approaches to this problem in the literature. One thing you can do that's was the state of the art for a long time is to assume some distribution on the bidder's valuations and compute an optimal reserve price, and then just sell the items to everybody that has at least this value for the item. But then people became interested in worst case analysis of the auction. So we don't want to make any assumption on the distribution of the valuations. And in this case, you can there are several approaches. One is an online approach that you assume the bidders are coming in an online fashion, and at every bid you offer them a posted price, and they either take it or leave it, and then the next person comes and you offer another posted price. And the approach we're going to be taking here is called competitive auctions, and I'll define this in the next slide. So this approach of competitive auctions was initiated by a paper of Goldberg, Hartline, and Wright in, I think, SOTA 2001.
what's the difference between a reserve price and a posted price?
So a reserve price is something that you take some assumption about the distribution of the agents and you compute the optimal reserve price, and then you post that price for everybody. You don't change it as the agents come. It's not online. The posted price is online, and it works in a worst case scenario. So you don't assume a distribution on the bid valuations.
The posted price is still online before your agent arrives. So I post the price, the next agent arrives.
Then you change
my
it, yeah.
price. There's a reserve price you're never allowed to change.
Yeah.
Do you still allow, assume that there is an unknown distribution, or can the distribution change with time? Or?
In the online posted price work, that's a worst case setting. So it's like online algorithms, and you want to have a competitive ratio with the optimal guy that knows the future. You assume any arbitrary setting of the future bidders' valuations, and you want to compete with the optimal auctioneer that happened to know the bidders that would come in the future. And you should restrict this optional auctioneer in some way in order to make the competitive ratio feasible. I think they get something like the optimal fixed price, some constant times the optimal fixed price, minus an additive factor that depends on the number of bidders in the market. So it's yeah. So yeah. You have to pick a measure of comparison that you can say something about, I guess. And so we'll talk a little bit more about the optimal auctioneer in the next slide. So competitive auctions, again, it has a sort of analogy to online algorithms and the analysis of online algorithms. I want to get approximately as much revenue as an omniscient auctioneer while having a truthful auction, okay? So assume every agent has a value in the range 1 to h, and the values are decreasing. And this is just for convenience of writing the next couple of bounds. A competitive auction, we wanted to get as much revenue as an omniscient auctioneer, and our factors are going to depend on how we define this omniscient auctioneer. So one possible definition is that the omniscient auctioneer gets exactly the optimal profit. He knows everybody's valuation, he can charge everybody their valuation, and he can get this profit. As Ryan guessed, this is hard for us to compete with, so we're going to define instead the optimal fixed price auctioneer. So this guy is going to pick some price, and then the number of items he sells, one copy of the item to everybody whose valuation was higher than that price. So he picks the VI that maximizes I times VI, where the VIs are ordered in decreasing order, as in this slide. You can note that the optimal fixed price is at most a log H factor from the optimal profit. You can see this by looking at the bids as they fall into buckets of like 2 to the I and 2 to the I plus 1. And one of these buckets must contain, there are log H such buckets, and one of them must contain T over log H of the profit. And then you lose a factor of 2 by charging the price equal to the low end of this bucket. Again, both of these objectives are hard to compete with because you could have one high bidder that very much dominates the market. So if everybody bids $1 and somebody bids $1 million, you can't hope to get anywhere near $1 million in a truthful fashion because this guy could pretend he's a low bidder. So in the literature, people have defined a third optimal auctioneer that they want to compete with. And this is the optimal fixed price that sells at least K items. So this hides the bidder that has a very high valuation, and it doesn't hurt your competitive ratio. But in this talk, I'm going to focus on the second bullet. So you can forget now everything I've written except for the second bullet, the optimal fixed price, F. So people have been studying this for a while. The most recent work that achieves the best competitive ratio is a randomized auction due to Goldberg and Hartline. in SOTA 2003, and it gets a competitive factor of 1 over 3.39 F minus H. So this means that it always gets as like approximately a quarter of the revenue of the optimal fixed price auction. Okay, so that auction is randomized, and that is fine, but one very interesting question we can ask ourselves is if we can solve this problem deterministically. So can I find an auction that is deterministic and gets approximately as much revenue as the optimal auctioneer? Why do I want to ask this question? Well, first, it was raised as an open question in a paper of Goldberg, Hartline, and Wright in 2001. It's an interesting theoretical question because, well, a lot of times when you have a randomized algorithm, you ask yourselves how you might de-randomize it. And there's a lot of techniques that are developed for this. But in the context of auctions, these standard techniques fail to preserve truthfulness. So there are randomized auctions that use even just one bit of randomness. But if you try to, say, run the auction with the heads and run the auction with the tails and take the one with better revenue, this is not going to be bit independent anymore. Finally, there are some economic incentives for defining deterministic auctions. For one, it reduces the risk to the auctioneer. So for a risk-averse auctioneer, you can guarantee that he gets at least so much revenue instead of getting so much revenue with high probability. Okay, so this is a very interesting question, but there's also this impossibility result. It says that there is no constant, competitive, truthful, symmetric, deterministic auction. And this gives you some, this result made a lot of people think that, well, therefore there are no deterministic auctions. And that's why all of the all of the auctions in this field so far have been randomized. So what does this statement mean? Okay, by constant competitive, I mean that it gets 1 over alpha fraction of the optimal fixed price for some fixed alpha. Truthful, I mean that it's your dominant strategy to tell the truth. Deterministic means that it's not randomized. And symmetric means that the auction doesn't look at your identity when it computes your price. So in other words, that bid-independent function is just a function of the values of the other bidders, the actual numbers of the other bidders, as opposed to their identities or the order in which they were submitted. Okay, so how can we prove this theorem? Consider two valuations, just a low type and a high type. So this theorem holds even with just two valuation types. And consider this bid-independent price function. It's a function of the number of bids and the number of ones and the number of h's only. And it outputs a price that's 1 or h. Yes?
That's not
Symmetric, yeah. And I am assuming it outputs a price that's 1 or h, but that's without loss of generality, because if it outputs something lower than 1, there's no reason not to output 1. And something between 1 and h, I might as well bump it up to h. And something higher than h, it's not going to get any revenue from, so I might as well lower it to h. Okay, so notice that f depends only on the number of ones in the input. Now, consider the following picture. Here I have the number of ones in the input of f on the x-axis and the number of h's in the input of f on the y-axis. And at each point here, that function f must have some value. So in order for the auction to be constant competitive, it must be the case at the bottom spot here that when the bid input is all ones, it must be offering a price of 1. Otherwise, it would have 0 revenue. And when the bid input is all h's, it must be offering a price of h. So somewhere along here, I flipped from offering a price of 1 to offering a price of h. Okay, now consider the bid vector where there are x ones and y h's. What's going to happen in this bid vector? Well, consider an agent with bid 1. When we remove him, there are x minus 1 ones and y h's. So the function is going to offer him a price of h. Therefore, we get 0 revenue from this guy. Now consider an agent with bid h. When we remove him, the function is going to offer him a price of 1. So the revenue of the deterministic auction is y. But the revenue of the optimal auction is at least y times h, because it can charge the price of y. And therefore, we aren't h competitive.
H is not a constant?
Yeah, h is, I don't know h as the auctioneer.
But one of these other results, you were, out some constant competitive minus 8. But
Okay.
H is not a constant, then how is that really?
So that's, you can think of that as the promise that the revenue of,
That revenue is at least a constant.
yeah, the best revenue is at least a constant h. And that's how I'm getting around the fact that if there was one high bidder, I couldn't compete with him because, I mean, I couldn't compete with the optimal fixed price because his, I can't charge him $1 million if he's the only guy bidding $1 million, truthfully. Okay, so to get around this deterministic impossibility result, we have the idea to use asymmetry. You have to use asymmetry in some way. And how might we do this with the case of 2 bid values? Well, consider the following bid input vector, sequence of 1s and h's. If you wanted to do this in a randomized auction, you could simply flip a coin for every guy and charge him h with probability 1/2 and 1 with probability 1/2. And that would get you half the h's at h and half the bids at 1. So how could we do this deterministically? Well, the idea is to make all the h's have a partner h. So we're going to pair up all the h's. And we'd like to get half of the, each partner, we'd like to get one partner at the price of h and one partner at the price of 1. Of course, we have to do this bid independently. So we cover up a bid, and we don't know if this bid is a 1 or an h, but if it's an h, we'd like to know who its partner is. So in order to compute that, we count the number of h's to the left. It's even, and therefore the partner must be on the right. Now that we know who the partner is, we have to coordinate whether we're going to charge this partner a 1 and that partner an h, or vice versa. So we need some quantity that they can both agree on without knowing their own valuation. And that quantity is the number of 1s between the two of them. So in this case, there's an even number of 1s between the two of them. And it means that I can make a decision tree that says when the number of h's to my left is even, the number of 1s between me and the next h to my right is even, I'm going to decide to charge a price of h. Now, what do I do about the partner? The next bid sees an odd number of h's to the left, so it assumes its partner is to the left. Now, it looks the number of 1s between this place and the h to the left is even. So the decision tree says if the number of h's on your left is odd and the number of 1s to the next h on your left is even, charge a price of 1. Okay? So this is clearly going to have the property that every other h is offered a price of h, or half of the h's are offered a price of h. What about the other bids?
A lot of us have been doing this problem.
I've heard.
Blue-red shirt problem.
So we can, for this guy, he has to do the same thing that the h's are doing, because we don't know if his price is a 1 or an h. He looks to the left, there's an even number of h's. He looks to the right for a partner h, and he finds that guy. And he says the number of 1s between me and that guy is even, so I'm going to charge a price of h. And the next one is going to see an odd number of 1s between him and the partner h, and is therefore going to charge a price of 1. So you see that in a sequence of 1s, the 1s alternate between a price of 1 and h. Okay, so the properties, the theorem here is that we're getting at least half the optimal revenue minus h. And the argument is, as I said, half of the H's get the price of H, and half of all the bids get a price of at least 1. So if the optimal revenue was H, we were fine. If the optimal revenue was 1, we're also fine. Okay, now I'd like to digress to a fun little problem called the hat problem. Yeah?
It feels to me like you're pushing the randomness off into this order, and the bidder doesn't know the order. And that, from the bidder's point of view, that lack of information is going to make it.
It doesn't matter if the bidder knows the order. It's still, it's a bid-independent function. So he can't affect the order. We're assuming he can't affect his order.
If I know I'm fifth, and I know the rest of the bid, then I can bid 1 when my evaluation of bid, I know there's something else.
But your price assignment doesn't depend on your bid input. When we were computing these, we were covering up your bid input. We computed this price of H without seeing that you were bidding a 1 or an H. So it
So even knowing the order doesn't help.
yeah, but being able to affect the order helps you. But
So that complicates my strategy, right? So if I can bid first, effectively.
yeah, well, you have to, for example, assign every bidder an identity and then ask for the bids.
But that identity doesn't matter.
It doesn't have to be. It can be arbitrary.
No, I don't think that's where it's going, no.
So you can fix them all.
It is, I mean, that's like, it is actually,
What we're getting from the randomness is now what we're getting from the arbitrariness.
Yeah, we're getting it.
I shouldn't
We're getting the randomness from the asymmetry of the input. You'll see another example of this, and maybe it'll get clear. So I'm going to talk now about a problem called the hat problem. So you have a party, and you have n people and n hats that you pass out to these people as they walk in the door, and each hat has one of k colors. And let's say person I wears a hat of color BI. So you can't see the color of your own hat, it's on your head. And the game is that you want to guess the color of your hat, even though you can't see it. And you can't ask people what the color of your hat is. That's cheating. So the party goers win the game if collectively at least 1 over k people of each hat color correctly determine their hat color. Okay? So there's a very easy randomized solution that works in expectation. You flip a k-sided coin and guess the color that the coin came up, and then you expect 1 over k of every hat color class to get their hat color correct. But how do you do this deterministically? The idea is to construct a bipartite graph, and then we're going to look at a fractional flow in this graph, conclude that there is an integral flow, and construct the deterministic solution from the integral flow. So the graph is as follows. It's a bipartite graph. On the left, I'm going to have all the nodes that correspond to the scenarios that a party goer might face. So in this bid, party goer number 1 faces a scenario in which he sees that 2 and 3 are wearing a blue hat, 4 and 5 are wearing a green hat, and so on. Here, party goer number 6 sees that party goer number 1 is wearing a red hat, party number 2 is wearing a blue hat, and so on. So in general, our nodes are indexed by n-1 colors, and they're missing a particular index color I. So to make sure you've understood the construction, you should be able to see from a counting argument that there are n times k to the n minus 1 nodes on the left of this bipartite graph. Okay, what about the right? On the right, I'm going to put all possible scenarios that happened at the party along with a guess. So here, the scenario is that the first guy was actually wearing a green hat, the second guy was actually wearing a blue hat, and so on, and the guess of somebody was green. And I'm going to draw an edge between two nodes if the scenario is consistent with the truth and the guess is correct. So there's an edge between these two nodes because party goer number 1 saw what the node on the right says the actual situation was, and party goer number 1 guessed green, and he actually was wearing a green hat. Similarly, you're going to have a node that says what happened if the question mark was really a blue hat, and he guessed blue, and a node and edge for when the question mark was really a red hat, and he guessed red. So again, counting argument to make sure you've understood this, the degree of the nodes on the left is k. What about the degree of the nodes on the right? The degree of a node with a guess red is going to be the number of reds in this scenario vector here. Okay. So in general, I have a node indexed by some particular color, x, and a sequence of bits, or of colors, sorry, of n colors. And there's going to be an edge between two nodes if the colors are the same everywhere on the two nodes, and the question mark color is equal to x, and this x is in the ith spot in the node on the right. And I can refer to such a node as v sub xb in my slides. Okay, now I'm going to connect a source to all the nodes on the left and a sink to all the nodes on the right. And I'm going to imagine that the capacity of these edges is as follows. All the edges of the bipartite graph have capacity 1. All the edges out of the source have capacity 1. And all the edges into the sink have capacity equal to the floor of the number of x's in the scenario over k. So in particular, if we manage to saturate the capacity out of every node on the right, we will have won the game. So consider the following fractional flow. I send unit 1 of capacity on every edge out of the source, 1 over k out of every edge on the sink, on the left-hand side of the bipartite graph. I argued that the degree of every node here was k, so this conserves flow. And then since the in degree of every node on the right was the number of colors over k, the fractional flow will have these values on the edges into the sink. So this fractional flow satisfies all the capacities out of the source, all of the capacities in the bipartite graph, but it might violate some capacities into the sink. But it can violate them by at most 1 over k. So I can push back the flow 1 over k along a path and still have all flow on edges being positive and construct a fractional flow that saturates all the capacities into the sink. This means that the edges into the sink form a min cut, and all the capacities are integral. So I know there must be an integral flow, which also saturates all the capacities into the sink. So this integral flow looks something like follows. I have some edges out of the source, some 1, some 0. Out of every node on the left, I have some 1s and 0s. And into the sink, I saturate the capacities. So I have floor of the number of x's over k. So how does this solve our problem? Well, if you give every party goer a very big index card with this graph, the party goer can look at the node that corresponds to the scenario that he is facing, and he guesses a color corresponding to the edge labeled 1 out of his node. Or if they're all 0, he can arbitrarily guess green, say. And why does this win our game? Well, how many correct guesses are we going to get? Look at this scenario that was the truth in the party. Say it was the blue, 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 green, green node, the second node there. It means that I get number of B's over K of the B's at B, because that's how much capacity is coming out of that node, and I know that capacity is saturated. And similarly, I'm going to have another node with the same scenario, but a green guess that is going to tell me that I get 1 over K of the greens at green, and a red node with red guess. So I get 1 over the K of the reds at red. Okay, so this has given us a deterministic solution to the hat problem. How does that help us with the auction problem? Yeah?
So what are you saying about this deterministic solution?
I'm saying that a floor of 1 over K of each hat color class will guess their hat color at its color. So out of this node here, if this were the real scenario that was happening at the party, then how many people are going to guess red? It's the number of ones coming into here, right?
Are you guaranteeing that 1 over K of the guesses are correct?
Yes, yes.
So
But something stronger than that. In fact, 1 over K of each color class has a correct guess. Up to the floor.
Can you give an example where you have 4 people, 2 colors, and how you're guaranteeing that they all, they're either red or green, and you're giving me an algorithm where they necessarily get the red color?
Sure. So you should draw this graph. So you have a node that has question mark red, red, red. Then you have n times k to the n minus 1 nodes here, right? And then you can draw a flow. You have to use the integral flow theorem. There's a fractional flow that saturates all of the capacities out of the edges here. And then we know that since the capacities are integral, I can find an integral flow. Okay?
This is a small n, so you will use a lot on the floor.
I mean, I'm saturating all of these capacities. I'm getting...
Yeah, but it will not give 1 over K, of course. It will give 1 over K.
Oh, it gives 1 over K up to the floor of each color class, yes.
So I guess then this is essentially an exponential algorithm.
Yes.
And this is a solution. So is that a
Yes, so the second half of my talk is going to be dedicated to a polynomial time construction. But it's not, I mean, it doesn't, it should correspond to some integral flow, I guess. But you can't just see the integral flow from the solution that I'll give you that's polynomial. This is going to work for any number of hat colors. The solution I'll give you later will only work for 2 hat colors.
But so what's confusing to me about this is that so you're not using the information about what really happens.
I am using it when I'm constructing the integral flow. I'm using the information about what happened in the randomized solution in order to guarantee that I can construct an integral flow.
But okay, so this solution. Okay, so here's what I'm not understanding. You give me a solution and you guarantee that 1 over K of them are correct. So I'm going to take all the people that were correct and then split them. Right? What's changing in that?
The node that you're looking at will change. If you have the first and third guy were correct and they switch their hat, then they're going to see a blue here and a red here, and this question mark might change his guess. Okay. This is the most difficult slide in the talk. So how does this help us de-randomize auctions? You can imagine that the hat colors were the bids of the people. So I have bids and prices. I round them down to the nearest power of 2. This gives me log H hat colors. Okay? And I lose at most a factor in 2 of the revenue. And then I can simulate the previous construction. So I look at this step where I was constructing the fractional flow. I construct the graph with these log H hat colors. When I was constructing the fractional flow, I put on the edges of the bipartite graph the probability that the auction guessed the price of the agent correctly. So it's like the auction guessed the hat color. Okay. And on the edges into the sink, I put the expected number of bids which the auction guessed correctly. Okay, so this is very much like the fractional flow in the previous case. The randomized auction there was to flip a 1 over k-sided coin, and that's why I had 1 over k on all of those edges in my fractional flow in the previous slide. And let's call this value in my notation, I'll call this EJ sub B. So EJ sub B is the expected number of bids that the randomized auction guesses at their bid value. Now I want to argue that there is an integral flow with high revenue. So what is the revenue of the integral flow? It's the capacity of the edges that are going into the sink times the price at which I charge those bids. So it's 2 to the j times this EJ sub B up to a floor. And that is at least 2 to the j times EJ sub B minus 2 to the j. So I lose something because of the floor here. And now we're stuck, because I would love to say that this summation, this part of the summation, is close to the revenue of the auction that I was de-randomizing. But in fact, I'm only giving myself credit for bids which get I'm only giving myself credit when the price equals the bid. Okay? I was only giving myself credit for people who guessed their hat color correctly. But in fact, the auction gets revenue from people that even if it charges them less than their bid, not equal to their bid. So this isn't too much of a stumbling block. We can get around this with a trick we call guessing auctions. So I'm going to take any randomized auction, and I'm going to show you a reduction to a guessing auction, where a guessing auction only receives revenue from the bids that it guesses correctly. And by here, guess correctly, I mean it guesses the largest power of 2 that fits underneath the bid. I need to do this. If I could do this, I can use the previous construction to bound the revenue of the integral flow, because the guessing auction is, in fact, only getting credit for the bids that it guesses at the right value. So that summation is precisely the revenue of the expected revenue of the guessing auction. So what I need to show you is that this reduction doesn't lose too much in revenue. So how can I do that? Well, I define a guessing auction for any auction, randomized auction A, as follows. I simulate A on the bids. And then if the price that A offers bidder I is PI, I'm going to offer some price perhaps a little bit higher than PI with some probability. So I offer the largest power of 2 that fits into PI with high probability. And then with probabilities that are slightly decreasing, I offer slightly higher prices. So in expectation, I should be doing well here. And the lemma we can prove is that the expected revenue of this guessing auction is at least a quarter of the expected revenue of the auction, the randomized auction. And how do we show that? It's not so difficult. Suppose that a bidder wins at price PI in A. I want to show that in expectation, I'm going to get something close to PI from this bidder. So let K be the largest integer that fits into this price PI. And let J be the bucket into which the bidder's valuation falls. Now, the guessing auction is only going to get revenue when it offers that bidder a price of 2 to the k plus j, right? But the probability that we offer 2 to the k plus j, by definition of the guessing auction, is 2 to the j minus 1. And the payoff, if I actually manage to guess 2 to the k plus j, is 2 to the k plus j. And therefore, in expectation, I am getting a revenue of 2 to the k minus 1, which is at least the price over 4. So I've shown you that this randomized auction, called a guessing auction, gets almost as much revenue as the auction itself, the auction I was trying to de-randomize. And that gives me the following theorem, which is joint work with Gagan Agarwal, Amos Fiat, Andrew Goldberg, Jason Hartline, and Madhu Sudan. Corresponding to any single round sealed bid auction, perhaps randomized, with expected revenue E of A, this construction will give us a deterministic auction that has expected revenue at least 1/4 that of A minus 2H.
But if it is deterministic, why is there expectation?
This is just in the bound. This is the expected revenue of A. That's some value. I'm saying that the auction that I'm designing will get at least this much revenue.
But the guessing auction that you described was random.
Yes, so maybe I should have put a double prime here. I'm using that flow solution to de-randomize the guessing auction. So the structure is I take the randomized auction, I define the guessing auction, perform the reduction to the guessing auction, I de-randomize the guessing auction. So using that best randomized auction from many slides back, it gives us this corollary that we know that an existence of a deterministic auction whose expected profit is at least this. Okay, this result, let's recap. I just said it in words, but let me put it on the slide, how we actually get this result. We design a deterministic auction for general bid values. That was our original goal. We provide a framework for de-randomizing the randomized auction by converting a randomized auction to a random guessing auction, representing the choices of this guessing auction by fractional flow in a graph, and then finding an integral flow in the same graph. And then this integral flow will tell us how to charge every agent deterministically. This is nice. It proves existence, but the construction is exponential. So this result is good in the sense that it tells us something about the power of randomness in auction design. It tells us that we can sort of trade off randomness for asymmetry. It also gives us a general construction for de-randomizing auctions. And as we find better randomized auctions, we prove the existence of better deterministic ones. And it also introduces some techniques that might be useful in other de-randomization scenarios. But it has this drawback that its construction is exponential and raises the question of, is there a polynomial time construction? So the next result, which is very recent work I am going to show you, is a polynomial time construction for this particular problem of digital goods auctions. In order to give you this polynomial construction, I'm first going to show you a randomized one and then tell you how I can run the same auction deterministically. So the randomized auction is based on this idea called the cost-sharing auction, introduced by Mullen and Schenker. Suppose you knew the optimal revenue F. Then you could define the following auction. You look at all the bidders. You see if they can all pay a price equal to F over N. If they can't, you kick them out. And you look at the remaining bidders and you offer them a price of F over the size of the remaining set. If all the bidders, as soon as all the bidders accept, you stop the algorithm and that's your output. Okay, so this is called the cost-sharing auction. It has revenue F. That's clear because you know that this revenue was achievable by a fixed price. So you'll find that fixed price. And furthermore, it's truthful. This you can see because it's bid independent. It can be computed bid independently. You just assume that your bid is infinity, and you run this, or if you want to do it independent of the ith bidder's bid, you set his bid to infinity, and you run this cost-sharing auction, and then you've come up with some price. If he was a winner, then that price is going to be something he can afford. It's going to be the right price. And if he was a loser, you don't care what happens. So this is truthful. And the problem with it, the reason that we can't use it to design an auction is, of course, we can't compute this optimal revenue f. But suppose we can compute some other function, r, bid independently, such that r is close to f, and every bidder agrees on this revenue r, that this target revenue r. Okay, so the idea is we're going to try and cost share this target revenue r. In that case, we could use this auction to cost share this target revenue, and we would achieve this target revenue. Okay, so we can't hope to, I mean, it's hard to find a function such that these are equal for all I and j, so the second condition is difficult for us. But let's see what we can do. Let's let r be the revenue of the optimal single price on this set of bids, b minus I. Well, then if we assume that f has k winners, then we know that the optimal single price is at most f. If the bidder I that we're removing was a loser, we can still get revenue f. And it's at least k minus 1 times f over k if the bidder that we're removing was a winner. So in particular, it's close to f. And furthermore, if we assume that f has at least 2 winners, then we know that these values of r for every bidder, they might not be equal, but they're close to each other. In fact, their minimum is at most twice the maximum. The maximum is at most twice the minimum. Okay, so how does that help us? Well, consider the following picture. I know that this value r that everybody's computing spans at most 1 power of 2. And furthermore, the minimum endpoint is at least half the optimal revenue, and the maximum endpoint is the optimal revenue. Now, I want to round this function r I'm going to find this new function, r prime, which I'm going to round the revenue r that I defined before, either to the closest even power of 2 or the closest odd power of 2. So if I round it to the closest even power of 2, you see that people disagree on what revenue they're trying to cost share. Say j was even. So some people are going to round to 2 to the j, and other people are going to round to 2 to the j minus 2. So they're going to be trying to achieve different revenues, and the cost-sharing algorithm is not going to get possibly not even any revenue. But if they happen to round to the nearest odd power of 2, then everybody rounds to the same value. So they're all trying to cost share the same amount of money, and this means that they will successfully cost share it. So with probability 1/2, they're trying to cost share 2 to the, well, I'm multiplying by 2 here in order to improve my constant. So with probability 1/2, they're trying to cost share 2 to the j. And they can achieve this. So consider the winners in the cost share of 2 to the j. In expectation, half of them are going to try to cost share this revenue. And so from these, we're going to generate 1/2 2 to the j in revenue. And this is 1/4 of f. Okay? Here, we use the assumption that f sells at least 2 items in order to prove that this interval spans just 1 power of 2. This result appeared in Goldberg, Hartline, and Soda 2003. And this is actually the best randomized auction for this problem. And we'd like to present a deterministic auction that's based on this randomized one. So in particular, we need this coin flipping to have the property we used of the randomness was that half of the winners flipped to heads and half of the winners flipped to tails. So maybe we can deterministically label the bidders in such a way that half of the bidders are labeled with half of the winners are labeled with the heads, and half of the winners are labeled with the tails. So consider the sorted order of the bids. You know that the winners appear in the prefix of this sorted order. So we need a function such that for any prefix of this sorted order, half of the bids are labeled with a plus and half of the bids are labeled with a minus. We call this set balanced. And I'm going to define for you a function that is balanced. So this is just supposed to give you some intuition about how we developed this function. We knew it had to use the asymmetry of the setting, and it should use the properties of the entire bid sequence. This will become clear when I show you the function. The function is as follows. I'm going to compute -1 to the I, so the parity of the index of the bidder that I'm trying to come up with a labeling for, and multiply that by the sign of the permutation which sorts the remaining bids. Okay? So the lemma is that for all prefixes, this function is balanced. And the proof is fairly simple. So consider a sorted sequence of bids, and consider transpositions between adjacent elements. So the sorted sequence of bids satisfies this. I'm going to show that any transposition flips everybody's sign, and therefore any transposition satisfies this. So if you want to prove this property of some particular bid vector, you just perform transpositions from the sorted vector in order to make it into the bid vector. And if you always perform transpositions between adjacent non-equal elements, you will preserve this property throughout the whole transformation. And why is that? Okay, so consider these two elements, x and y, and consider transposing them. When you transpose them, the sign of the permutation that they see, in fact, when you remove them, remains the same. So the sign of the permutation remains the same. But the parity of their index flips, because x moved down one spot and y moved up one spot. And therefore, their assignment flips. Okay, for all other elements, the index remains the same. We've only transposed x and y, but the sign of the permutation that they see changes by a transposition. So the sign changes and the assignment flips. Okay, that gives us a way to derandomize the following auction, the previous auction, that I showed you, the randomized one.
Are you saying that this is also truthful?
Yes, this is truthful. I'm using the bid independence here to say it's truthful. I'm computing this labeling, a plus or minus 1, for a particular bidder I without looking at his bid value. This f is a function only of the...
Isn't I his... I is not the sorted way. I see, okay.
So using this to as the heads and tails in the previous randomized algorithm I showed you, it gives us a deterministic algorithm that generates at least 1/4 of the optimal revenue minus h. And the proof is similar to the randomized proof. Okay, so that concludes the main part of my talk. I have this slide here mentioning some open problems related to this work that I've done. So first you saw this exponential-sized graph for derandomizing any randomized auction. But it only used, whenever we wanted to compute the results for a particular auction, we only looked at a polynomial subgraph of this graph. So is there some way you can compute the integral flow without writing down the entire graph? And you have to do this in a way that everybody computes the same integral flow. So we tried this for a while. It seems very difficult. But I think this would be nice if we could do this. And it would, in particular, imply a solution for the hats problem. Which a solution for the hats problem might be easier. Perhaps you can use some of the parity techniques that we used for the heads-tails labeling to get a solution to the hats problem. Or even less ambitiously, it would be nice to see if you could find a way to label such that everybody gets one of 3 values. and it's balanced in that sense that I had before. And all of these problems, I think, should have very elegant solutions. I don't know how to solve them. That's it.
I really apologize, but I got to go back to that.
Sure.
So everybody goes into the party and they all get this exponential size card.
I think they all get told who they are as well.
So I know who I am and I know my card. Everybody has the same card. Although the card's not defined to everybody.
You can write them down beforehand.
Other people, and for you, they're
As soon as you know N and K, you can write down this card.
But the cards are individual.
They're the same for everybody.
They're the same for everybody.
But everybody also gets told who they are. Where on the card?
Okay, I don't know.
Oh, you have a card which covers everything, and then you know who you
Your
are.
individual rule is different.
But so we could, instead of a card, we could have one card on a projector that everybody gets to look at.
Sure.
Okay?
And you
So
know where to start.
what's confusing to me is that the way the problem was set up, is I go to a party and I have no idea what's going to happen. There's this rule that I can't talk to anybody. But what you're telling me is if I change my hat to a different color, the graph that we all see changes.
No, it doesn't change. Just the node that you're considering in the graph changes.
The whole
My node has to stay the same.
no.
Okay, so that means that there is information about the color of my hat in that graph.
Yes.
So although we can't communicate directly about it, we're kind of
All
implicitly.
possibilities.
Seeing this graph doesn't help you.
It does though, right? It tells
I mean, it tells you what to guess,
You
but
don't need to get the whole graph of it. Because get only the node in the graph that corresponds to saying if you think this and that, this is that. You can't get a list of options what to think, the same thing as what to
And you
every
know your
person
change.
gets a different list of options.
I see. So we can each get a polynomial graph.
No.
My
But you
sub.
run the
No,
whole.
Over the options, some graphical system, because there are exponentially many options for the next of the other.
I think you're right.
Exponent better.
Okay.
Okay, so that means that if I change my hat color, my card stays the same, but everybody else is.
yeah, if you want to, or you can write down the entire card. Yeah.
Right.
The node that your view of the world changes. So these two nodes are identical, aren't they? These two nodes shouldn't be identical, but if the first person changed to a blue hat, then this guy might have been looking at this node when this first person was wearing a red hat, but if there was a B here, when the person wore a blue hat, he should start looking at this node instead. And he follows the one out of this node to figure out what to guess when he's here. And when he's looking at this scenario, he follows an edge one out of this node to see what to guess. It could go to a different color. It's very weird that it works, but
But most importantly, two people who see exactly the same selection of hats can get differently because they're different people wearing that hat.
yeah.
That's where the asymmetry is.
Yes?
Is there some notion of something like fairness? I mean, I suppose that the agent may demand that you should have the same chance of winning.
Yeah, so Well, you're not going to like this, but you could have a random permutation of the agents.
But in a sense, yeah, you traded randomization for fairness. I mean, for asymmetry, which is therefore for fair. I mean, for symmetry, right? Fair.
Like Paul said, I mean, it's still fair to the players, but also the auction is still deterministic, so it's, risk-free.
Yeah,
No,
that's
no, but does not necessarily work. So how do you know that the last of taking because the bids are
why doesn't the random permutation
because
help
it
you?
depends on what the other bids are.
But so okay, if it's symmetric, so it's randomized.
No, but the bidders are not symmetric. I mean, there is one particular bidder who always bids blue, and one always bids green. So the bidders are not symmetric.
But the guess, the node that you're looking at would change. So your guess would change. You have a
Yes,
chance of getting the right guess.
So maybe this notion of fairness is that if I have the same valuation and then you still get you, then we'll sort of have the same chance.
Yeah, yeah.
Which would be satisfied if you did a random permutation, whereas without.
We introduced randomization back again.
Yeah.
But you still, like, as Ryan said, you aren't risking losing revenue. You still have that worst case guarantee.
That's good for Mike. We can claim that we're fair.
We decided that.
You all look alike.
We have to believe that randomness is fair.
Hmm?
We just discussed that for elections. People think that randomness is